All right, good afternoon. Brian Trammell. I'm with the Network Situational Awareness Group at CERT at the Software Engineering Institute at Carnegie Mellon University in Pittsburgh. Very long prepositional phrase to parse through there. Talk today is going to be on preparing allocation and assignment data from the RIRs for network security analysis tasks. A little bit of background. We do analysis on various security incident data from various intrusion detection systems and traffic analysis data or flows. All of the actors in this data are expressed by IP address, which, that's how all this is expressed, but we'd like to be able to do analysis operations at higher levels of abstraction, for example, by location, by organization, and by network. So we use allocation and assignment data from the RIRs to bridge the gap between the IP addresses in the incident and traffic analysis data and the levels at which we'd like to do analysis. So we set out to build a tool. We figured it'd be pretty quick, nice little Perl script. The requirements were to first group addresses into CIDR blocks, that being the contiguous range of addresses that can be expressed with a single CIDR prefix. For each of these blocks, we wanted to provide a network name, a country code, tech and administrative point of contact handles. And we wanted to group these into a tree, an allocation and assignment tree of the entire worldwide IPv4 address space. The reason to do this is this allows us to associate an address in our input data with a network at any level of allocation for assignment, from the top level allocation all the way down to the lowest sub-assignment. Yes, you'll notice we're talking about IPv4 here. We don't get any data about IPv6 networks yet, so there was no requirement to handle that. Also, we want our collection system to run periodically because it's used for batch analysis and we require very little operational support, essentially a cron job that one person can manage in their spare time. So for example, using a RIPE near real-time database mirror to get RIPE objects in would be overkill. So we go out and we get bulk who-is data from 3 of the 4 RIRs at this point. From Aaron, we have an agreement with them, and the RIPE and APNIC INET-NUM databases are publicly available. You'll notice LACNIC is missing from this list. As of the time that I put this presentation together, we were still working on getting a bulk data request set up with them. I've been informed that that's gone through, so in the next couple of weeks we will have data from all 4 RIRs. When you do see numbers in this presentation, they refer only to the 3 RIRs for which we have data right now. So as of May 5th, when this was put together, there were a little over 2 million ranges, which map to a little over 2.1 million CIDR blocks. We assumed in all of these ranges that, 1, the allocation tree is strictly a tree. There are no overlaps in ranges such that you can't determine which range is higher in the hierarchy than another. That is not true in all cases. We made the assumption that the registries agree on every allocation. That's mostly true, but it's not true in all cases. We assumed that all allocations and assignments were done in terms of single CIDR blocks, which is true in most cases, but not all. And we assumed that all supplementary information, particularly we're interested in modification dates because we're looking at using that to disambiguate some of these things. We assume that those modification dates are stored in a universally uniform format, which they mostly are, but sometimes are not. So the tool chain that we put together, which processes this allocation data, performs a set of transformation. First takes the modification dates, puts them all into a common format, eliminates redirect records. For example, Aaron has records that point to space that is allocated by the other RIRs, so that when you go and make an Aaron who-is request, it either redirects through our who-is or gives you a nice helpful little pointer that tells you go ask RIPE, for example. We resolved outstanding conflicts between regional registries. We'll see those in a second. We take the allocations and put them into a single tree structure. There are some anomalies that we detected that I'll be talking about in a moment in doing this. The 2 interesting classes of these are erosions, which are off by 1 errors at the ends of each range, and inversions, which are points in the tree where the tree hierarchy is violated and there's an ambiguity as to which range is higher or lower. It turns out that a lot of these are actually erosions. And then after we've done all this, we've stacked things into a tree, we split the allocation ranges into CIDR blocks. So the first step is to get the information from the ARN and RIP formats, which are different object formats, into a common format. At this point, we normalize the modification dates. Most of the oddities here were some dates in assignments where years were given as 2-digit years to 4-digit years. Those are pretty easy to disambiguate. There are a couple of places we noticed the date format was year, day, month as opposed to year, month, day. We were only able to fix these where that was unambiguous. So for example, May 9th, if that happened to be stored in this format, we couldn't fix it. And there were also 4 instances where there was a date beyond the end of the month. For example, April 31st. I have no idea what's going on there. Then we go through, strip out the redirect records because they do not represent actual networks that we're interested in, and they will be covered when we merge data in from the other RIRs. So each stage of merging merges from 2 registries into a single tree. We do this in multiple stages in order to build a unified allocation tree of the world IPv4 space. At this point, we use an algorithm to resolve conflicts between the registries. And most of these are cases where both ARN and either RIP or APNIC have records for the same range. In that case, we go with the registry that's affiliated with the country associated with that range. In 3 cases, that doesn't work. So for example, I think there's one where ARN says that a net range is allocated in France, and RIP says it's allocated in the United States. So we very arbitrarily chose to go with the oldest registry. So ARN wins in that case. There's no real reason behind choosing this other than to keep from having human intervention in this process. So after we've got a single unified list of ranges, we correct the erosions. I'll be showing an example of that in a second. Then we stack the ranges into a tree. So we build the tree out in memory. We take a look at the depth of each range in the tree. The reason this is important is later on we're going to split them into CIDR blocks. Now if you happen to have an allocation that is 4 blocks wide and it underneath it has an allocation that is 2 blocks wide, let's say a /24, /23, and a /24, and then underneath that there's something that has 2 /24s on it. That first /24 is, once we do the block splitting into CIDR blocks, we won't be able to tell which of those /24s was originally higher in the allocation hierarchy. We also detect inversions at this point. We'll be seeing examples of those in a second. And once we've resolved all of these anomalies, each range record is replaced with 1 range per CIDR block that's covered by the record. It turns out that 99.98% of allocation ranges are actually in terms of CIDR blocks, so the growth in the number of records is relatively small. As we saw, it's 2.06 to 2.12 million. So the first of the 2 types of anomalies that we found in the ranges are erosions. These can be further classified as inner or outer erosions. An inner erosion is where a net block is missing either its network or broadcast address, either or both. So for example, 10.230/24 shows up as 10.231 through 10.23254. This is a problem because we like splitting things into CIDR blocks. 10.230 through 10.23255 splits into 1 block, and 10.231 through 10.23254 splits into 14. So we'd like to correct that to make our block-oriented view of the world a little cleaner. Also, we make the assumption that since 99.98% of ranges are allocated in terms of CIDR blocks, if something looks very much like a CIDR block, then it probably is. At the same time, we see outer erosions, which is where the last address in a range is actually expressed as the first address of the next range. So it's treating the end of range, which is supposed to be treated as inclusive, as non-inclusive. This causes an inversion when we try to stack the tree together, because the tree stacking algorithm cannot determine whether the first range or the second range, which share an address at this point, which of those two is supposed to be on top. So here's a picture to illustrate an inner erosion. You'll see a single network we will call A, it's a /24. If it's eroded, it could split into as many as 14 blocks when we attempt to split it. So we fix it by nudging the edges out to match the block boundaries. An outer erosion, here's how this can cause trouble with tree stacking. When you have two, for example, /25s next to each other, they obviously are next to each other in the hierarchy, and there is a parent allocation above that. However, if one of them has, like, so here B is expressed as .0 through .128, and C is expressed as .128 through .255, they invert with each other. They share an address, the ends of the ranges overlap, and that breaks the tree hierarchy. So out of those 2.1 million blocks that we found from the data from these 3 RIRs, we found 6,400 erosions. Most of those are inner erosions. The ones that are outer erosions, the vast majority of those are at the end of the range. For example, as I said, the end of range is not inclusive. We see 457 instances of ranges that are shifted by 1 in either direction. So, for example, /24 as x.y.z.1 through x.y.z plus 1.0. I'm not exactly sure what's going on there. I have to take a deeper look at what's causing that. Almost all of these on /24s are smaller. The erosion detection and correction algorithm does not work on anything smaller than a /28. The reasoning behind this is, so for example, a /29 is 8 addresses wide. So when you're correcting erosions, you're correcting them correcting that range to either a size of 6, 7, 8, 9, or 10, because you could be adding or subtracting 1 on either end. The thinking here is that you're far more likely to false positive on correcting an erosion and actually adjusting an endpoint when the endpoint doesn't really need to be adjusted on something smaller than a /28, although we'll see that that assumption is not quite right later on when we look at range inversions. So an inverted range is one that doesn't fit cleanly into the tree. As we saw here, this is an example of an inversion caused by an outer erosion. These may indicate errors in allocation ranges. They may indicate that there are stale allocation or assignment records that have not been pulled out. So for example, if you have 2 ranges that have been assigned, those go away. Another range comes in and takes all of the first range and half of the second range. If those 2 haven't been removed from the database, then it's ambiguous as to which of those is correct. So yes, it is difficult, if it's even possible, to know which range in an inversion is correct. I need to do a little bit more work here to figure out how to fix that up. The current procedure, in order to continue on without human intervention, just drops the second range as it's sorted. So here's a picture of an inversion. This arrangement's a little contrived. You wouldn't see this much subassignment typically, but let's play along. So here's a /24 that's been assigned down into 2 /25s, one of which is assigned into 2 /26s, one of which has part of it reassigned as a /27. If, for example, E there is allocated as a range of 2 blocks, a /26 and a /27, and F is the same /26, they share a range of addresses, and it's ambiguous as to which one of those is correct. So there are 745 of these detected in the data. One case, at least one case I found, was what looks like a typographical error in the range. So we have a couple of /29s next to each other, but the third octet is off by 1 in either the beginning of range or end of range. So when these are put on top of each other, there's a significant overlap. Now, you could look at this and say, yeah, these are both probably /29s, but you can't tell whether it's the beginning of the range or the end of the range that has the typo in it without a little bit more context. There are a lot that are also just a simple overlap. Again, a couple of ranges may share 6 or 7 addresses, and it's unclear as to which of those is correct. There also are outer erosions I've looked at in the data that are outer erosions on tiny blocks, either /29s. I think there are a couple of /30s that have outer erosions on them, and they're not fixed by the erosion process, because when you go in and you adjust the parameters on the erosion detection and correction algorithm, you end up with a whole lot of false positives, particularly, I think, in spaces that are pre-CIDR allocation. So you'll notice here that there are no counts by type. Right now, range inversions are categorized by printing them all out and taking a look at them. I don't have algorithms quite yet for distinguishing these types of inversions from each other. So the toolchain does drop an anomaly log at each stage. This was used first for tuning of the anomaly detection and correction techniques for generating the data in this presentation. And also could be transformed into a useful format for reporting these anomalies to the registries for possibly correcting that data, although there's more work that needs to be done before that's possible. So future work, inversions need a way to categorize them, need a way to correct them in an unambiguous way. It seems that it would be possible to use context to look at the ranges that are allocated around a range that we suspect is eroded in order to minimize the detection, false detection of erosions, and use other types of context so that we can actually look at very small erosions, fix them, and thereby resolve some of the inversions in the data. Erosion detection on multiple block ranges. Right now, we only look at ranges that are a single CIDR block wide. Looking at the data for inversions, there are several, at least, ranges that are, say, maybe a slash. Well, I'm not even going to guess here. But there are some that are multiple block ranges that we'd like to be able to detect erosions on. And also working on submitting anomaly data to the RIRs. So if you'd like more information, if you'd like to take a look at the software, which is essentially a collection of Perl scripts driven by a makefile, you can take a look at aircert.sourceforge.net/addertree. So any questions?
Hi, Brian. Tom Best, no fixed address. 3 questions, actually. I thought this is great. I struggle with some of this stuff myself. First question. What is your sense of the semantics of the use of the country codings by the registries, if you have any sense of the meaning behind them? Second question, how confident are you of the current status of the contact data and the other data that's in the registries? And third question, have you had a chance to map your registration data against what's actually currently in the routing table now, and how many ASNs are not covered? Because right. I've had some observations about this.
Okay, what was the first question again?
Semantics of the country coding by the registry.
The semantics of the country coding are essentially the mailing address of the organization that manages the network, or the mailing address of the admin handle. The admin handle is, I believe, universally assumed to be on site at the network. But yeah, we're aware that that's not 100% A-OK for geolocation, but it is in some cases better than looking just at the allocation maps, because in a lot of cases assignments are done across international boundaries. Like, for example, a lot of European ISPs have African customers, and there are a lot of African countries that don't show up in the allocation maps that do have addresses assigned to them. So this is better than the allocation maps, but not as good as it could be. Okay, second question.
Second question, the timeliness and accuracy of the contact information in the
Right.
RIR databases.
We're sort of cheating here. We don't really care at this point. We are using the contact, we're using this primarily to aggregate instant and traffic reporting data, not, for example, to actually get down to an abuse handle that we could contact. So as long as for a given network or a given set of networks, the admin handles are reasonably up to date and we can aggregate by those, that's good enough for our purposes. We are aware that that's an area for concern.
I think there are fixes in the works for that. Third question,
yes.
then, comparing what your results are against actually what's in the routing table.
Yeah, we'd like to do this. We just haven't gotten around to taking BGP feeds and taking a look at them.
You will find that there may be as many as 2,000 autonomous systems that are routed, which are not covered by the registry data.
Excellent. Good to know. Thank you.
You're welcome. Thank you very much.
Any others? All right.
Brian, thank you.